Welcome to Dr. Boxy Teaches Special Topics in Mathematics. In today's lesson, we will look at a proof that pi is irrational. So let us get started. So what we want to do is to prove that pi is irrational. And the way we will approach it is by assuming that it is rational, in other words, that it can be written as the fraction of two integers. Now, because we know that pi is a positive number, we may as well assume that the numerator and denominator, a and b, are themselves positive numbers. And let us take the fraction to be as simplified as possible, so without any common prime factors. If they do have common prime factors, just simplify the fraction and call the simplified fraction a over b. So what will we actually do in this proof? I will sketch it before I actually do it because it is quite long. So the idea is the following. We will use the numbers a and b to define a function, which I will define on the next slide, which I will call fn of x. And I'll show that the integral of fn of x multiplied with sine of x between 0 and pi is on the one hand an integer, and on the other hand strictly between 0 and 1. That will be the contradiction that will lead us to the conclusion that the assumption that it is a fraction is untrue. Now, showing that that integral is strictly between 0 and 1 is easy and short, and that will be the end of the proof. The majority of what I'll show you, the vast majority, will be in an argument to come to the conclusion that that integral is an integer. That will take us multiple slides, and let us get started with that. We start with the assumption that pi can be written as the fraction a over b, and we will use these numbers a and b to define a function fn of x, where x can be any real number and n is any strictly positive integer, and the definition of fnx is a minus b x to the power n multiplied with x to the n divided by n factorial. Now, to prove that the integral of this fn multiplied with sine of x between 0 and pi is an integer, we will need a whole list of properties of this function fn. The first one is that plugging in 0 into the function just gives us 0. The reason for that is there is a term x to the power n, and so plugging in 0 just makes everything vanish. The second property is that fn is a polynomial. The reason for that is the following. The binomial theorem tells us that a minus bx to the power n can be written as some coefficient multiplied with x to the 0th power plus another coefficient multiplied with x to the first power, etc., plus all the way to a coefficient multiplied with x to the power n. That is what the binomial theorem tells us. And if we now multiply this a minus bx to the power n with x to the n, which is the numerator of the function fnx, we get a coefficient multiplied with x to the n plus another coefficient multiplied with x to the n plus 1, plus all the way up to a coefficient multiplied with x to the power 2n. And now we still have to divide it by n factorial, but n factorial is a number, it doesn't depend on x, so all it will do is change the coefficients in front of the x's. It won't actually change the fact that it is a polynomial. And not only is it a polynomial, it's a polynomial of degree 2n, and there are no terms in this polynomial of degree smaller than n. So this is the second property. The third property is that fn of pi minus x is equal to fn of x. How can we see that? Well, if we want to calculate fn of pi minus x, all we need to do is to take the definition of fn of x, and everywhere where we have an x, we just replace it by pi minus x, which is what I did in this statement here. Every x has been replaced by pi minus x. Now, we also know what pi is. Pi is a over b, and so I replace the pi's by a over b. Now, in the numerator on the left factor, we can bring in the b into the bracket, and so we get a minus b times a over b, so that's a, so a minus a cancels out, and we're left with minus b times minus x, so that's bx to the power n, so that's b to the n times x to the n, and everything else remains as it was. And now we can bring in the b to the power n into the brackets, and so it cancels with the b in the denominator in the first term, and the second one just becomes bx, and so we get this expression, and this is exactly the definition of fn. So this proves that fn of pi minus x is indeed equal to fn of x. That's the third property. The fourth property is that fn of pi is 0. This is easy to see with what we already have now. Fn of pi is, of course, the same thing as fn of pi minus 0. And according to property 3, this is the same as fn of 0, which according to property 1 is 0. So that proves the fourth property. The fifth property is that the kth derivative of fn evaluated at 0 is an integer for any k. Now, to prove this, we will distinguish three cases. The first one is the case that k is strictly smaller than n. Now, why is in that case fn k, the kth derivative of fn at 0, why is that an integer? Well, that follows from property 2. Remember, we know that fn of x is a polynomial of degree 2n, but with no terms of degree smaller than n. So if the number of derivatives, the number of times we take the derivative of fn is smaller than n, all of the terms still contain x to the power of something which is strictly positive. So all of the terms still contain x's in them, which means that when we plug in 0 into that expression, we will get 0, which is an integer. So for k strictly smaller than n, we know this to be true. It's true that it's an integer. The second case is if k is strictly larger than 2n. Well, in that case, it's even simpler. Fn is a polynomial of degree 2n, and if we take its derivative more than 2n times, all the terms vanish, and so everything is 0, even before plugging in 0. And so especially it's true that the kth derivative in this case at 0 is an integer. It's namely 0. The only case that is left is what happens in between them. In case k is between n and 2n, we need to actually calculate this k derivative to see that it's an integer. So to do that, we take the definition of fn of x and we use the binomial theorem. So the x to the n divided by n factorial remains, but the a minus bx to the power n, I use the binomial theorem to write it as I did here, where the ni that you see here is the combinatorial factor, which is defined, nk is defined as n factorial divided by k factorial multiplied with n minus k factorial, and that is always an integer. Now, there are multiple ways we can see that. One of the ways is that the interpretation of nk is the number of ways that we can choose k objects out of a total of n objects. And now the number of ways you can do something is always an integer. So now we can still rewrite this a little bit. The sum remains, the ni remains, the negative one, the negative in the brackets at the right, I just pulled it to the front, so we get minus 1 to the power I, and the n factorial, which was in the denominator outside the sum, I just brought it into the sum, so we get minus 1 to the power I divided by n factorial. The a to the power n minus I remains, b to the power I remains, and we already had an x to the I in the sum, but there was also an x to the n outside of the sum, and so taking them together gives us x to the power n plus I inside the sum. And now we want to take the kth derivative of this. Now notice that each of those terms are just, it's a sum of numbers multiplied with x to some power. And so when we take its derivative, when you take the derivative of x to the fifth, for instance, you get 5 times x to the fourth. So the coefficient, the exponent comes to the front as a coefficient, and the degree of the exponent decreases by 1. If you take another derivative, you get 5 times 4 multiplied with x to the third. If you keep on doing that k times, you get that x to the power n plus I, the kth derivative of that, is either 0 if the number of times you take its derivative is strictly larger than the degree of x. If you keep on taking a derivative and k is strictly larger than the degree, than n plus I, then you just get 0. And that means that in the sum, all the terms with I strictly smaller than k minus n will vanish, which is why the sum starts in this case at k minus n and not at 0 like before. And if k is less than or equal to n plus I, well, in that case, the number of times you take a derivative is less than or equal to the degree of x, and all you get is x to the power of n plus I minus the number of times you took the derivative, so it's x to the power n plus I minus k. and the coefficients in front of them are all the coefficients that you brought to the front. So the first time you brought it to the front, you got an n plus I in front of it. The next time you got an n plus I minus 1, n plus I minus 2, etc. And the last time, the kth time you took a derivative, what came to the front is n plus I minus k plus 1. And so we get this expression here, where one more remark is the expression that you see here is simply equal to this coefficient here in front of it. It's just a different way of writing it, because the coefficient at the bottom here is n plus I times n plus I minus 1 times n plus I minus 2, etc. But it doesn't go all the way to 1, it goes to n plus I minus k plus 1. We can write it as n plus I factorial, meaning that it actually goes all the way to 1, if we divide it by all the terms, all the factors that we actually added there. So if we let it go, instead of stopping at n plus I minus k plus 1, we let it go to n plus I minus k, n plus I minus k minus 1, n plus I minus k minus 2, etc. We can add them in denominator and numerator. And in that case, we get exactly this expression here. So the expression I circled in the kth derivative of fn is simply another way of writing the coefficients in front of the x to the power. What we want to show is that the kth derivative of fn at 0 is an integer. So what we do is we plug in 0 into this expression. Now when we do that, all the terms in this sum, you have a sum of some coefficients with x to some power, and all the x to strictly positive powers will simply vanish when we plug in 0 into x. The only term out of this whole sum that will survive is the one where I is equal to k minus n, because in that case what we have here is an x to the power 0, which is just 1, so there is no x in it, and therefore that is the only term that will survive. That means that the only term that survives is the coefficient in front of this x to the power n plus I minus k for I equal to k minus n. So everywhere where we see an I in this expression, we just replace it by k minus n, which gives us this expression here. Now 0 factorial is just 1. And we can rewrite it in the following way. The combinatorial factor remains. Minus 1 to the power k minus n remains. All I did was bring the n factorial in the denominator to the end. So we get k factorial over n factorial. Now my claim is that this is an integer. Now why is that so? Well, look at this multiplication here. The combinatorial factor n k minus n is, as I said before, always an integer. Minus 1 to some power is an integer. A and b were integers themselves, and n and k are integers. In other words, an integer to an integer power is itself an integer. So everything except for the very last fraction, the k factorial over n factorial, everything else before that is an integer. Now why is k factorial divided by n factorial also an integer? The reason is we are considering the case here where k is larger than or equal to n. But therefore, k factorial divided by n factorial can be written as k times k minus 1 times k minus 2, etc., all the way to k minus n plus 1, and all the terms after that are cancelled out by the n factorial in the denominator. And so we're left with this multiplication here, but all of these are integers, which means that k factorial over n factorial, because k is larger than or equal to n, is itself also an integer. That concludes the proof that the kth derivative of fn at 0 is an integer no matter what k is. We're not done yet. We still need an additional property of fn, namely that its kth derivative also at pi is an integer. Now, once we know that the kth derivative at 0 is an integer, property 5, proving this is not difficult anymore. So we know property 3 tells us that the function evaluated at x or evaluated at pi minus x is the same. But that means that its kth derivative is also the same. Now, the kth derivative of fn evaluated at pi minus x, fn evaluated at pi minus x is actually a composition of functions, and so its kth derivative, we need to use the chain rule k times. And so we get the kth derivative of fn itself evaluated at pi minus x multiplied with the kth derivative of pi minus x of the argument of fn. And the kth derivative of pi minus x, every time you take a derivative you get a minus 1, and so you get minus 1 to the power k. Now if we evaluate this at pi, if we evaluate this at 0, what we get is the kth derivative of fn at 0 is the kth derivative of fn evaluated at pi minus 0, so at pi, multiplied with minus 1 to the power k. So that's minus 1 to the power k multiplied with the kth derivative evaluated at pi. And now the left-hand side of this equality is an integer by property 5. And so what we find is that what we want to show, namely the kth derivative of fn at pi, multiplied with minus 1 to some power, is an integer. But if something multiplied with minus 1 to some power is an integer, it itself is an integer as well. And so we have that the kth derivative of fn at pi is also an integer. We now have the properties of fn that we needed, but we are going to have a couple of steps more, and we define a new function g of n. And by now you probably are thinking there's no way this is going somewhere. I guarantee you this is going somewhere. Bear with me for a couple of more slides, we're almost done. We define the function gn of x in the following way. It's an alternating sum of the even derivatives of fn, where the 0th derivative is just the function itself. And we can rewrite this gn in the following way. And we will look at a couple of properties of this gn also. The first property is that gn of 0 is itself an integer. The reason is if we plug in 0 to the definition of gn, well, fn of 0 is 0, so an integer, and all the other terms are derivatives, or even derivatives, but so derivatives of fn evaluated at 0. Property 5 tells us that it itself is an integer. Property 8 is that gn at pi is an integer, and the argument is exactly the same. Properties 4 and 6 together tell us that the first term and all the consecutive terms, all of them are integers themselves. The final property of gn we need is that gn plus its second derivative is fn itself. Why is that so? Well, gn is defined in the following way, and if we take the second derivative, each of the terms get derived twice, and so the first term fn derived twice gives us the second derivative of fn, the next one minus the second derivative of fn becomes minus the fourth derivative of fn, etc. And the very last term becomes minus 1 to the power n times the 2n plus 2 derivative of fn. Now remember that property 2 tells us that fn itself is a polynomial of degree 2n, which means that if we take a derivative of a degree higher than the degree of the polynomial, it just cancels out. And so the very last derivative is 0, it vanishes. And what happens now if we add gn and the second derivative of gn? Well, what we will get is the following. This term here, negative the second derivative of fn, will cancel with this term, the positive second derivative of fn. Here we get a fourth derivative of fn and negative fourth derivative of fn, etc. All the terms cancel out except for the very first one, fn of x. And so what we find is indeed that gn of x plus the second derivative of gn is fn itself. Now, how can we use all of this to prove that the integral of fn multiplied with sine of x between 0 and pi is itself an integer? Well, if we look at the derivative of this expression here, what do we get? Well, this is a sum of two products, and so if we take its derivative, we will get four terms. The first term will be the second derivative of g multiplied with sine. The second term will be the first derivative of g multiplied with the derivative of sine, which is cosine. The third term will be minus the first derivative of g multiplied with cosine. And the fourth term will be minus gn times the derivative of cosine, which is negative sine. And so the negative with a negative becomes positive. The last term is plus gn of x sine of x. Notice that the two middle terms, the second and the third term, cancel out. And so we're left with the first and the last term that have sine x in common, which we can bring out of the brackets. And the thing within the brackets now, property 9 tells us that that is simply fn. So we get this expression. So the thing we started with, the derivative of that expression, is simply fn times the sine. But that means that the integral of fn times the sine from 0 to pi, well, what we can do is just replace fn of sine, fnx times sine, with this whole expression here. And we get the integral of a derivative, which by the fundamental theorem of calculus tells us that that is just the thing within the derivative evaluated at the boundaries. So when we evaluate it at pi, we get the first derivative of gn at pi times sine of pi minus the gn at pi multiplied with cosine of pi minus that expression again evaluated at 0. So the first derivative of g at 0 times sine of 0, and then minus minus, so plus gn evaluated at 0 times the cosine of 0. Now the very first term has a sine pi in it. Sine pi is 0, so that term vanishes. The third term has a sine of 0 in it. That term vanishes as well. Sine 0 is 0. The second term is negative gn pi multiplied with cosine of pi. Now cosine of pi is negative 1, so it cancels the negative in front of it, and we're left with gn of pi times 1. And then cosine of 0 is 1, so we get plus gn of 0. But so we find that this integral, the integral fnx sine x between 0 and pi, is actually equal to gn pi plus gn of 0. Properties 7 and 8 tell us that both of these terms are integers, which means that that sum itself is an integer. So we finally found that this integral is an integer. We now have to prove that that integral is strictly between 0 and 1, and as I mentioned at the very start of the video, that is much shorter and much quicker. So first of all, the range of integration is between 0 and pi, and pi is a over b. If we now multiply in the expression x is less than a over b everything by b, we get that bx is less than a. In other words, a minus bx is larger than 0. Now that means that fn itself is larger than 0, because fn is a minus bx to the power n, which is positive according to what we just saw. X itself is between 0 and pi, so it's positive, and a power of it is positive as well, and dividing it by n factorial, which is a positive number, doesn't change the fact that it's positive. So fnx in this region, in this range of integration, is positive. Secondly, in the same range of integration, sine x is between 0 and 1. In other words, it is positive as well. And from that, it follows that the integral, because the integrand is positive in the range, in the whole range, the integral itself is also strictly positive. So that proves one side of that inequality. Now we want to find an upper bound for the integral. To do that, we start by just writing out fn. And now we will do three things at once. First of all, x is between 0 and pi. In other words, sine x is between 0 and 1, which is what I wrote before. But that means that in the integrand, if I just get rid of the sine x, I actually make it bigger. So the first thing we will do is just get rid of sine, and that means that the result we will get will be larger than the actual integral. Secondly, x is less than pi and positive. In other words, x to the power n is less than pi to the power n, which means that if I replace the x to the n by pi to the n, I also make it larger. So that will be the second step. And the third step is the expression a minus bx, I can just replace it by a, because a minus bx is less than a. Bx is positive. In other words, if I replace a minus bx to the power n by a to the power n, I also make it larger. And so I did these three things here in this expression, going from the expression above to the one I just have here at the bottom. And notice that in the integrand here, there is no x left. And so the coefficient a to the n, pi to the n divided by n factorial can be pulled out of the integral. And the integral itself is just the integral of 1 dx, which is x, evaluated between pi and 0, which just gives us pi. In other words, this integral is equal to a to the n times pi to the n plus 1 divided by n factorial. And so we find that the integral that we're interested in, fn times s sine of x dx, between 0 and pi is strictly between 0 and this expression here. Now notice everything we've done until now was true for any n. But what can we say about this expression? Well, as n grows larger and larger, this expression goes to 0. The reason for that is that a factorial grows quicker than an exponential or a polynomial. And so the numerator, the denominator grows much quicker to infinity as n grows. A way to test this mathematically is, for instance, using the ratio test for sequences. But the fact that this is 0 means that if we take n large enough, this will be smaller than 1. In other words, there exists some m such that that expression is less than 1. And for that value of m, it is true that the integral of this fm with n replaced by this m is on the one hand strictly positive because that was true for all n's, and at the same time strictly less than a to the m times pi to the m plus 1 divided by m factorial, which is strictly less than 1. In other words, that integral is strictly between 0 and 1. This proves that it is between 0 and 1. As we saw before, it was an integer. An expression cannot be an integer and strictly between 0 and 1 at the same time, which proves that the original assumption, namely that pi can be written as the fraction a over b, is false. This is one of the many proofs that pi is an irrational number. I'll see you next time.